The topic is shapes and geometry of surfaces. What I'll do is try to define for you what we generally mean by surfaces, yeah, and then try to come to the other two terms in the title, shapes, geometry. So what are surfaces? So essentially, I mean, when we see, it's essentially the simplest way to say what surfaces are is, it's all visual information. So we, as human beings, we have eyes, so we look around. We don't see what's inside a tree, right? We just see the surface of the tree. So the surface of a tree, all these things that you see around you, crude visual input, these are surfaces. So how are we going to, but it's a huge amount of information. You just look around and, I mean, anytime you see something, you're seeing a surface. So that's a huge amount of information. But if you want to extract knowledge from it, some way of classifying it, understanding it, some understanding out of it, you'll have to have some scheme of saying that this surface is different from this surface. Yeah. So we do it instinctively. For the surface of a bag and the surface of a chair are different. Yeah. How do we formalize it? So what is it in our thinking process that distinguishes between surface of a chair, surface of a bag? Yeah. So that's the problem. I mean, we instinctively recognize it, but what is it that goes on in our brains that manages to accomplish this? What is the abstract structure that allows you to distinguish between different surfaces? So that's the problem that we are addressing. Yeah? So that finally, in order to talk about surfaces to other people, other mathematicians or human beings, I mean, in general, you should be able to communicate that information to another person so that the other person grasps what you are talking about, right? So it's conversion of some visual information into something that's more formal. The speech area of the human brain actually developed much later, during the course of evolution, right? So it's converting a visual symbol into something that's ordered. Words we say are ordered in time. I mean, it's converting a sort of a space organization into a temporal time organization. So that's something that's there when we try to extract formal structure out of any information that we have. Yeah? So that's really the abstract scientific problem that we have in front of us, and I'll try to give to you or tell you what mathematicians as part of science, I mean, see, the division of science into various disciplines is a relatively recent phenomenon. Yeah? So in the time of Newton, for instance, all of mathematics, physics, a bunch of them, all of it was called natural science. Yeah? Science dealing with nature. Because of limitations of our brain, when we want to probe into something, we have to divide science up into more specialized regimes so that one can go deeper into it. Yeah. So that's the result, I mean, that's the cause of this diversification of sciences into various disciplines. It's not a naturally occurring division. Yeah. Basically a limitation of our human brains. Okay, so we'll have to start with something fairly crude in the sense of visual information. I'll give you a few samples and then we'll try to see how we go about this problem of trying to organize and understand this information. Okay, good. So we start off with it. So we have a huge, I mean, anytime you look around, you see a huge amount of visual information around you, and these shapes around us comes in all shapes, all sizes. So here's a sample, the surface of a globe. This is one of the first regular shapes that one comes across, but there's a whole bunch of others. Here's something slightly more exotic, and these are models. I mean, what's curious to note here is that this object, this blob on top and the blob at the bottom, they are pretty large, but these connecting things are small. Here the blobs have become very small, but the connecting limbs are long. Okay? Here's a more exotic example. It's essentially, I mean, what you see in this golden yellow color on the boundary, that's what's called a knot. Yeah? You take a piece of string, tie it into a knot, splice the two ends together. So you have a pipe, tie it into a knot and drive one end into the other. That's the fringe, and this surface there's some exotic kind of surface which is spanning it, sitting inside three-dimensional space. Okay, so these are examples of a bunch of surfaces, things which we'll probably not see in everyday life, but nevertheless, we would like to organize all this visual information. So how do we go about doing it? What is a scheme? I mean, when we say that we want to understand surfaces, what really do we want to do? Yeah. So we'll have to have a formal structure. I mean, this is what we want to understand this. What does it mean? We want to put it into dockets. Yeah. So instead of having a huge amount of information, we'll say all these things which have certain features are called trees. Yeah. So basically, that's a way of organizing all information about trees. So okay, then in that case, when you see a tree which is slightly different from another one, you will still not fail to recognize it as a tree. So this is essentially the feature of organization that's going on. So how do we organize all this information? We need a formal structure. But in order to get a formal structure, we'll have to tell you what surfaces are. Visual information is too crude a notion to work with. Yeah? So we'll have to define for you what surfaces are. And here's a first approximating notion, things which are locally two-dimensional. So if you imagine yourself to be an ant crawling on the surface of a tree, then the local neighborhood that it looks around, it looks flat, right? It looks like a two-dimensional object. So even human beings, I mean, forget ants, human beings till relatively recently, we thought that the earth was flat. Why? Because when we look at the earth locally, it looks flat. So the surface of the earth appears to us naively to be a two-dimensional object. Yeah? Presumably, ants aren't equipped to look at the earth from outside, so they think of the earth as locally two-dimensional. Okay? So anything we see is certainly locally two-dimensional. So that is what an informal definition of a surface is, something that is locally two-dimensional. Where does it come from? It comes from all visual information. Now, so I have given you a tentative definition of what we are looking at. Yeah? And we would also like to understand what understanding means. Yeah? So we would like to understand all this information, which means we would like to classify it, put it into convenient dockets. When you actually understand and say all animal species, what you do is you divide it into phylum, phyla, genera, species, etc., etc. Right? It's a convenient form of classification, and then there are features which you extract and say if a certain creature satisfies these features, then you put it into a particular docket. Yeah? And then nowadays you have computers where you put all your information, where there's a large file, inside that there are sub-files and so on. So it's some kind of a tree structure. Yeah? So there's some large group and that's divided into small groups, and still further groups, and finally inside each group you have members of that file, right? So that's the kind of thing that we mean. So what does classification mean in this context? That's what we are going to go to next. So let's try to make this notion of classification more precise. What we want is the following. We want an exhaustive list. Think of these as a collection of files. Yeah? So this is an exhaustive list which satisfies two properties. Given a locally two-dimensional object, we want to say which object in the list it is. Okay? So for instance, you have say folders 1, 2, 3, and you are given a new two-dimensional object, you will know very precisely which of the folders 1, 2 or 3 in which you put it. Yeah? So what does it mean? You have a list that has two properties. It's exhaustive, which means that no new visual object that is thrown at you will lie outside this list, will fit into anything outside this collection of folders. Also, it should fit into exactly one folder. So two folders should not, one fellow should not be legitimately allowed to go into two things. Yeah? Because then there's going to be confusion. So we need a way of saying when two surfaces are the same. Basically, input two surfaces, crank an algorithm, crank a way of saying that They are either the same or they are different. Yeah? So we need this kind of a classification scheme. So let's start with examples of surfaces, and I'll say what it means for two surfaces to be the same. Yeah? How do you recognize two trees to be trees? Yeah? I mean, there are two very different trees right here. There's a banyan tree, there's a deodar tree. But we don't fail to recognize both of them as trees. What is it that is going on in our minds to recognize both of these objects as members of one community called a tree? Yeah. So we'll have to define for you these features which say that two surfaces are the same. We are really trying to probe the meaning of the word same here. Good. So let's look at the surface of a rabbit. So this is a rabbit which has been used for this finite element method. I mean, so these little pieces that are there, you take a surface of a rabbit made out of some kind of fabric, and then you look at its surface fairly closely. Say, look at some patch here, and then you blow it up. It looks like a two-dimensional flat patch, right? So the surface of a rabbit is also an example of a surface, yeah, locally two-dimensional object. And yeah, so this very crude form of classification is going to say that the surface of the rabbit and the surface of the sphere are the same. Sounds quite stretched, but really if you think of this rabbit as made out of rubber, yeah, say the surface of a balloon. So you have these balloons that are sold in the form of various exotic animals. And suppose you have this rabbit made out of a plastic balloon, and then then one usually ties strings here in order to create ears, string around the neck to create a head, tail, etc., etc. But then once you remove those strings and allow the balloon to relax, it's going to relax into a spherical shape. Yeah? So this very crude physical idea of moving, I mean, say removing things that were constricting it and allowing it to move and relax into another shape, that is what we are going to call same. Yeah? So let's try to make that notion of sameness fairly precise, and so we'll give formal definitions. Yeah? Roughly again, when are two objects the same? If you can deform one object, assume that it's made of rubber, yeah? All objects, surfaces, so you're allowed to squish things around so long as you don't tear. Yeah? Tearing is a discontinuous operation. Yeah? Pasting two things together is also going to change the configuration. Yeah? But you're allowed to move things continuously. Yeah? Deform things continuously. Yeah? So that's what we are going to really mean by saying two things are the same. So what's the formal definition? So a surface, mathematicians try to make things as impersonal as possible. So it's a surface is an example of what's called a two-dimensional manifold, which means that something that is locally two-dimensional. That two and this two are the same. Yeah? In the same sense as 2 is equal to 2. Okay? So a surface is an example of a two-dimensional manifold. This world that we live in is an example of a three-dimensional manifold. Why? Because we know that space is locally three-dimensional. Yeah? We don't know what the global geometry of the space that we live in is. Yeah? There are a whole bunch of candidates, but we don't know. Yeah? But two-dimensional surfaces on the earth, we have some understanding. There's no, I mean, yeah, in this particular sense, if we are inclined to be democratic, then there's nothing special about 2, there's nothing special about 3. You might as well talk about 15,000 dimensional manifolds, spaces which are locally 15,000 dimensional, right? So basically what this does is it reduces all this stuff, I mean all human visual information to the notion of two-dimensional manifolds. Yeah? So what we are interested in doing, extract it out, made the notion somewhat impersonal, and so the mathematical problem now becomes classify objects which are locally two-dimensional called two manifolds, also called surfaces classically. So the meaning of the statement is just what I told you right now. That's exactly right. So So I've given you a formal definition in the hope that there'll be one or two budding mathematicians in the audience, yeah? But if you're, if you don't, so what, this word here, locally homeomorphic, is in this world of deforming things, this is what we replace the word same by, okay? Okay, and what it means is that you can deform one to the other without cutting or tearing, okay? So that's what it means. Yes? Yeah, that's what I'm telling you. So homeomorphic means you can take one shape to another by continuously stretching and pulling without cutting into two pieces. Okay? Formally it means there's a, if there's anybody with a mathematical background in the audience, it's a one-to-one continuous map with a continuous inverse. Okay? If you like it that way, yeah. Yeah, go ahead. R2. R2 is this. The surface of the screen is R2. Locally two-dimensional. What is two dimensions? It's a real line in two directions. There's an x-axis, there's a y-axis. That's all. So that x-axis, y-axis, all the graphs that you drew in school, yeah, that's an example of R2. Okay. That's right. No, a cube does not have a discontinuity. If you look at the corner of a cube, assume it's made of rubber, and you squash it down, it's going to look nice and flat. Then all the surfaces are the same, right? Ah, good. So that's the first guess, that all surfaces are the same. So I'll come to this question, whether all surfaces are the same or not. Yeah. Yes. Yes. That's right. No, you should not give away the punchlines that I have in my talk. That is not, okay, so let me tell you, that is not the same as a sphere. So you have an answer to your question. Okay. So not all two-dimensional surfaces are the same. So question is, are there other examples apart from the sphere? Huh? And the answer is here. That's your example. That's your example, right? So you take and what is this? How do you get this? You take a long strip of paper, take the top edge and the bottom edge, paste those two together. You're going to get a nice long pipe, correct? Take the left circle of the pipe, the right circle of the pipe, paste them together. What do you get? You get a bicycle wheel, the tube of a bicycle wheel, right? This, it's got a name. Mathematicians don't like to call things by anthropomorphic names, yeah? So we try to call them by completely, I mean, we give ourselves this illusion that it's completely de-anthropomorphized, it's a completely objective thing. It's not really. At the end of it, finally, it's a human mathematician that does mathematics. However, the idea is to try to be as objective as possible. Yeah. So here's this guy's got a name. It's called a torus. Yeah. In cafes, you get donuts. The surface of a donut is an example. If you want, so the surface of a coffee cup, yeah, it's got this one handle. Again, you're asked to assume that it's made of rubber, right? So which means that the cup can be deformed into a disc. A cup is something like this, yeah? A bowl has something slightly larger. You flatten it out, it becomes a saucer. You flatten it completely non-functional cup, but it's just a surface of a round ball of flour or plasticine, yeah? So that can be flattened, and that's one side, and then you attach a handle to it, and the surface of that is the same thing, it's a torus. Yeah? So there's the standard thing that this field of mathematics which allows you to deform things continuously and still say these things are the same, that field of mathematics is called topology. Okay? So essentially it's popularly also called rubber sheet geometry. If you were asked, so what does geometry deal with? It deals with shapes, right? So suppose your shapes were actually made on rubber sheets, yeah, and you were allowed to deform things. So on a rubber sheet, you are allowed to deform things continuously, right? So the popular way of defining topology is that it's the field of mathematics which does not distinguish between a cup and a donut, all right? Why? Because you can take the surface of the cup, deform it, and you can get back a donut, right? So hopefully we've we've tried to say what homeomorphic meaning what same is. Yeah? It's only the two-dimensional surface that you're talking about. So everything that we are looking at is hollow. There is nothing three-dimensional in the picture. It's only the two-dimensional surface that we are talking about. So in fact, this tree, the surface of the tree is what we are studying, not what is inside. Yeah? So in fact, there is no inside or outside. I mean, it's just the surface that you're looking at. So that's the sense in which it's an abstraction. Okay? Fine. So here again, I'm re-emphasizing when two surfaces are the same. They are the same if this is a formal notion, one-to-one continuous map from the first surface to the second surface, such that the inverse map is also continuous. What does it mean? It means the intuitive idea is that you can deform the first surface to the second surface without tearing, without pasting things together. Okay? So what's an example? You take this dumbbell with 3 bells and then start stretching things out. The middle one starts becoming thinner, the next start becoming fatter, and then finally at the end you have a sphere, right? So this sphere and this dumbbell that you started off with, their surfaces are actually the same viewed from the lens of topology. Okay? So this is what two guys are same means. And now in this framework of topology, we'll have to say when two things are different. Yeah? And as was pointed out, there's a torus, the surface of a bicycle wheel or a donut, and there's the sphere. They are different. You cannot get from a sphere to a torus by deforming it. Why? Because there's some handle there. Yeah? A cup and a bowl, a cup with a handle and a bowl without a handle are not the same topological object. You can't go from if you're allowed a plasticine, you can make a bowl and you can crumple it and make it go back to a round ball, but unless you tear off another ball, make it into a handle and paste it to the original guy, you will not be able to get to a torus. Yeah? This is a very crude reasoning. There's a way of formalizing this, but we will not get into that. Yeah? Okay, so this is a continuous deformation. Here's another example. You take some wrinkled stone, and then you can start deforming it continuously, and then you get to a nice round lemon shape. Yeah? This is another example of a continuous deformation. So any rock that you see lying outside, yeah, typically is going to be the same as a ball. Yeah? The surface of a rock, anything that you see, typically is going to be the surface of a sphere. Yeah? You get more exotic things otherwise. So here's the problem, classify all shapes. So I think I've explained the problem to you. The problem is take all shapes, when are two the same, when one can be deformed to the other continuously. So assume that the thing is made of some extremely flexible material. And then, yeah, question? Yeah. No, try to understand that thing. Which basically, it means that, see, how do we do our classification? Yeah, how do we do our classification? All trees with this kind of leaf structure is a Gulmohar tree or something like that, right? Then you have a Gulmohar tree and a banyan tree and a deodar tree. All these three things fit together inside this concept that we have in our minds called a tree. Otherwise, we will be distinguishing between two Gulmohar trees. Yeah. No. We are trying to get at a structure to classify all shapes. How our mind does it, I have no idea. Yeah. That's a completely different, I mean, that's an area of what is called cognitive neuroscience, artificial intelligence, etc. etc. That's a relatively recent thing. Yeah. So what we are trying to do is we are trying to construct, if you like, a tree with one node at the top. It's called surfaces. Then we want to go down to the next set of nodes. Just this one level of a tree diagram is what we are looking at. Yeah? So forget that tree notion. Right now we want a series of dockets. Yeah? Phylum 1, phylum 2, phylum 3, phylum 4, etc., etc., etc. The sphere will fit into one One of them is going to be labeled sphere. Anything that can be continuously deformed to a sphere is labeled sphere, right? So the surface of a rock, the surface of a lemon, the surface of a bowl, all that fits into sphere. Yeah? Bicycle tube, yeah, just a sec. Bicycle tube, surface of a donut, all that fits into torus. Yeah? These two folders are disjoint. There's nothing that belongs to both. Is this all? Now that's the question we are asking. You take any surface, say they are the same if they are continuously deformable to the other, and then you choose one representative of that class. So for example, one Gulmohar tree. Under that, all Gulmohar trees fit. Right? That's a strategy that we are following. Yes, go ahead. Exactly. The point is that it's not just in the sphere folder that we have zillions of things. We have zillions of things in the torus folder, and as you will see, every folder contains equal.
And you have zillions of folders.
So how many folders we have is a more systematic thing. So that's what we are going to talk about. What is the collection of folders we have? That's the problem that we are looking at. So let's classify. Here's an example. Can you fit it into any of the previous dockets? So this is a pretzel. Okay, it's a relatively rarer object, but it's still one of these biscuits that, I mean, kind of things that you eat. It's got these three limbs poking out of it. Yeah, and it's of course, I mean, done in a fairly symmetric way. Those three ears are arranged symmetrically around it. Question: is this the same as the torus? Can you deform this fellow to a torus without cutting, tearing? What would be your guess? Yes or no? You think no? You think yes? Okay, good. So let's have votes. You are allowed to fold, twist, say, assume this is made of plasticine. So you can move it around continuously. Don't paste two parts of it together. Don't tear it up into two pieces. That's all that I'm saying. Is it the same as the sphere? Is it the same as the torus? Definitely not sphere. Good. But what about a torus? Yes, young friend here. What do you think? You think yes? Okay. Why do you think yes? I mean, suppose I removed one of those handles. It was just two. I mean, it was two of these things stuck together. Can you get it into just a ring? So if you can't get from 2 to 1, how can you get from 3 to 1? Yes, young lady here. You're allowed to fold, meaning you're allowed to bend. Yeah. So into one ring. Yes, no, how many say okay from here, from the younger students? How many say yes? You say yes. How about you? There was somebody had voted yes. So 3 people say yes. How many say no? Okay. You say no. Okay, fine. So I think there have been more votes for no. And if we are to go by democratic system, we should say that it's no. Unfortunately, mathematics does not respect that. Yeah? Either yes or no. Yeah? In fact, I think there was some set of lectures given by one of these hard scientists, and a person had come to look at the lecture. I mean, in America or Canada, there's this system. Somebody from outside the subject comes and attends the lecture. The person just to evaluate what the lecture was about, yeah, and how the teaching is. Yeah. So the person who sat in for the lecture was from either history or literature or something like that. Yeah? And the person who was giving the lecture was either in physics or mathematics. And some students would ask some questions, sir, is it this way? No, it's not that way. Or if somebody asked another question, yes, it is that way. Yeah? At the end, this person said, what did you say? Yeah, the lecture was fine, but you guys are very authoritarian. You don't allow any other opinions. Yeah, so that's the point. We don't allow opinions at all. Yeah, either it's true or it's false. Yeah, opinions don't matter. So the fact of the matter is that yes, this is really different from the torus. So we'll come to the mathematical statement a little later. But now, for the time being, let's try to do this exercise in continuous deformation just to get your visual intuition in order, in gear. What about this guy? But if you put it on top of each other, then you will be pasting two things in order to make it one. If you are bending it, it's still going to have one hole at the top, then there's going to be a hole in the middle, then there's going to be a hole at the bottom, right? Looking from the top is not the point. Whether it is the same or the entire two-dimensional surface. Yeah. That's right. So that's why it is not looking at it from one, I mean, see, for example, a one-dimensional line, you look at it very carefully from one end, it looks like a point. Yeah. So that's not what we are talking about. We are talking about the intrinsically one-dimensional object, not how you look at it. Yeah. No, what I'm trying to say is that the side is completely irrelevant. When you want to communicate to an architect, yeah, that this is how your building is supposed to look, yeah, do you say that it's from the front it looks like this and that's all information about the building? Then he'll just construct a wall and that's it, right? So you have to give the entire piece of information from all possible sides. We have three possible chosen things: front, back, front, side, top. Yeah, that's not everything. I mean, so basically what does it look intrinsically? What way we look at it is again introducing this completely irritating and irrelevant factor called the human observer into the situation. Yeah. We want to throw it away completely. That's not relevant. Yeah. What is it in itself? You give it the same right to exist as yourself. Right? So what is it intrinsically? You're saying that it's the same as the previous class? Okay, so we'll come to that a little later. What about this one? So think of these three pictures. This is something like a teapot but completely non-functional. Yeah? It's got a round sphere, completely round sphere, on which you have added three handles. Yeah? So a three-handled teapot without a spout. Yeah? That's what this guy is. And now you have these three other guys. So these three fellows. Are they same amongst each other? Are they different from each other? Where you are allowed twisting and turning. Yeah? Are they the same as the torus? Are they the same as the sphere? That's the question that I'm asking.
All of them are same.
Pardon me?
Teapot is same.
Teapot and this guy are the same.
Yeah.
And what about this guy in the middle? They're different. Okay. This is also the same. So all these three are the same. Oops. All these three are the same. This is what you're saying. Yeah. What about the torus? I mean, basically what is this object? You take three bicycle wheels, yeah, cut out a patch from each of them. So cut, when we were students in college, I mean, very often our bicycles used to develop punctures, yeah. So you cut out that and then you put a round patch on top, yeah. Instead of putting a round patch on that, you take two bicycle wheels, cut out two round discs and put a cylinder in between. That's how you tube together two bicycle tubes. So that will be two of them. Instead of two, if you do three, you are going to get this middle picture. Yeah. So this stuff in the middle here, this is one bicycle tube, this is one bicycle tube. You've cut out a round disc, pasted the two discs, the two circle boundaries of the discs together. And if you've done three of them, then you get this guy. Yeah. So are these three pictures the same or different? And I need an argument for that. In terms of continuous deformation.
All of them can be deformed.
Each other. All three. Yeah. Why? Yes. How? Yes? Yes? This is the pretzel picture. Yeah. Yeah. That's right. So you can just take that middle portion, bloat it up into a sphere and you have this teapot with three handles. Very good. Very good. That's why the first picture and the last picture are the same. What about the first picture and the second picture? I want students to say this. Batao bhai. So now you're saying 3 holes in this object. Yeah? And that should decide everything. Okay, good. That's a very good guess. So you stretch this fellow out, that fat fellow here, this becomes flat and broad, and then you can slide the side in, right? Good. So that means these 3 pictures are pictures of the same object as far as topology is concerned. Yes? And now, in some local part, this was a sphere. Take a small disk there, put in any 2-dimensional surface that you liked. Surface of a rock, surface of a lemon, surface of a tree, whatever you like. So all those zillions of pictures that you had for a sphere are also there here, locally. Yeah. So the multitude of locally 2-dimensional spheres and the locally 2-dimensional this 3-hole teapot pictures, that is not really different. It's just that in nature, typically you have spheres occurring more naturally for a physical reason. But when you go to this abstraction, yeah, when you do not allow physical laws to function, then that multitude does not change. You take a tree, take its stem, plant it inside on the surface of this 3-hole teapot, and you know that the surface of the tree is going to be just that surface branched out into a sphere. That's all. Yeah. Okay. So these 3 objects are the same. Good. And here's the fact. This is the mathematical theorem. Somebody here guessed 3 holes, right? That number 3 is exactly what classifies. Yeah? So we call them handles. Why? Because mathematicians are not constricted by notions of functionality. So we call this a sphere with n handles. So where n is equal to 3. Yeah? A sphere with 0 handles is a sphere. A sphere with 1 handle on top, yeah, is exactly what a torus is. A sphere with 2 handles is 2 of these guys pasted together, yeah, which is something we have omitted. Sphere with 3 handles is what is going on here. So in general, there's nothing special about 3 again, so you can put 457 handles if you like. Yeah. So each positive integer union 0 defines for you a topological type of closed surfaces. Yeah? Theorem, these are all your folders. Yeah? We wanted a classification scheme, we wanted a collection of folders. Now those folders are labeled by simple things. First folder labeled 0, second folder labeled 1, third folder labeled 3, 557th folder labeled 57 plus 1 because we started with 0. Yeah? And so on. 57 is labeled 57 minus 1, right? So 0, 1, 2, 3, 4, 5, 6, etc., as far as you can go, infinitely off. Yeah. So here's the mathematical theorem. Any closed, I've used one extra word, orientable here. Yeah. I'll say what orientability means. But if you have a surface which closes in on itself, just note that the sphere doesn't have a hole sitting anywhere. Yeah. You have an ant. It does not fall off, as our ancients used to think. If you go by ship on the surface of the earth, at some point you'll fall off the surface of the earth. That's garbage, right? So that the garbageness of that input is used in this definition. You don't fall off your surface anywhere, right? You can continue infinitely often, and then because it's closed, you're going to come back to where you started off. Yeah? That's exactly what happens on the surface of the earth. Though I don't know how many people have actually tried it. Okay, so any closed orientable surface is homeomorphic to, remember that homeomorphic means this continuous deformation, yeah? Is homeomorphic to a sphere with n handles attached to it, yeah? Where n is a number 0, 1, 2, 3, 4 up to infinity, okay? So for each n, any number, any positive integer you think of, there is a class, there is a docket, there is a folder, yeah? And that's it. So the mathematical theorem says that's it, with this extra hypothesis of what's called orientability. So we'll have to say a little more about what does orientable mean. Roughly what it means is that the surface has well-defined sides. So, if you have a sphere, there is a well-defined inside, there is a well-defined outside. Yeah? Are there surfaces where an inside and an outside are not well-defined? A disk is something which does not satisfy this closeness property, right? So, you will fall off the edge of the disk. You travel at a constant rate, you just fall off. So, a closed surface, think of a closed surface which does not have a well-defined notion of an inside or an outside. Yes? Something twisted. Oh, fantastic. So, people have come here knowing mathematics. This is not fair. Okay, good. So, the Mobius strip is, well, yes and no. I'll show you. So, it is twisted. And why is there? So, this is an example of, this is a painting by Escher, Maurice Escher. So, what is it? So, these are ants. I mean, he did not draw ants crawling on it just because it looked exotic. There's a mathematical reason why he drew ants. Yeah. You look at the middle leg of the ant. Yeah. So, the ant sits on the surface. Its middle leg is something like a normal direction pointing outward. Right? So, think so mathematicians would remove the ants from the picture, they would just draw normals. Yeah? So, we're very unimaginative bunch of creatures. We want to remove all this extra stuff. And so, if there's just a normal here, then this ant would move around this Mobius strip with its middle leg pointed upward in the direction of the normal to the surface at that point, right? So, you start with this ant. All these ants are actually snapshots of the same ant. Yeah? That's what's explained by the picture. What is going on? So, this normal starts here. When it comes here, the normal is pointing in this direction. Then it goes below and you can see the bottom of the ant there. The normal is pointing into the board here. Then it starts, so it goes here, here, and then it comes out here. And then there's this normal direction pointing in this direction. Then it comes to this ant. The normal is pointing in this direction. When this ant, its body is touching this Mobius strip at the same point. Assume that the Mobius strip is made of flat paper. Yeah? So, there's a point, if it's a flat piece of paper with zero thickness, there's just one point where where the normal could be either upward or downward. Yeah? So, what has this ant done? It started at this point, it has moved continuously all around the Mobius strip till it comes to this position and then it goes here, and as you can see, the normal, the middle leg is going to point in the opposite direction to the direction from which it started. Correct? So, which means what? If you take a closed path, you start off at a point, you take a closed path, come back to the same point you started off with. The normal should point in the same direction that you started off with, is called an orientable surface. Orientation is just a direction of this perpendicular. Yeah? When you take a surface, you put in an orientation, means that you are choosing a direction of the normal to that surface. Yeah? Here, there is no well-defined notion of a normal. Yeah? This ant goes around a loop, starts at this point, comes back at the same point, but then itself it has flipped its in direction, right? So, this Mobius strip is a part of a surface. So, the Mobius strip still has an edge, so it doesn't quite comprise something that is closed. It has an edge. I mean, if there is this boundary circle at the boundary, yeah, it would fall off. Yeah? So, this doesn't quite fit into our classification scheme. However, it's an example which is non-orientable. Why? Because you start at a point, come back to the same point using a loop. This is not something that will going to go on in a disk. You take a point, take a closed loop on that disk, look at the ant, follow the ant around that, and it's going to come up right side up. Yeah? Okay? So, this is called a Mobius strip. You can build them up fairly simply. Take a piece of paper. Yes? Ah, fantastic. Come here. Show you. Yeah, show it to the audience. Is it glued up? Have you glued it up? No, he is not glued up. Excellent. Very good. So, you start off with this straight piece of paper. twist it just once, yeah, which means twist it through an angle of 180 degrees, right? And then you glue these two things together. Yeah. Now you start off at this point, follow this around. This is the ant. It comes back to my thumb in the opposite direction. Yeah. So when you come back to the point you started off with, the normal, that's what these ants are describing, that points in the opposite direction. So that's an example of a non-orientable surface. No, that's orientable, that's a cylinder, that's a much less interesting object. Okay, yes? That's a very good question. That's a very good question. So her question is that the notion of orientability as I have defined here, yeah, it requires one extra dimension, a direction in which to point your normal outside, right? So essentially what you are saying is that it requires the surface to be embedded in one extra dimension. That is a perfectly right question, and presumably the question you want to ask is there an intrinsic way? Because I have been emphasizing that you look at the fellow in itself, forgetting that we have the luxury of an extra dimension, yeah? Is there an intrinsic way of defining orientability and non-orientability? Answer, yes, there is. How do you define orientability and non-orientability? So, the crude way of talking about it is this right-hand thumb rule. What is it given by? In your two dimensions, you choose an x direction and a y direction locally. Yes? What is the outward normal? Go from the x to the y. This is this right-hand thumb rule. Yeah? So then the normal is in the positive normal is in the direction of your thumb. Yeah? This is a crude way of thinking about it. But it's one direction followed by the next direction. That order, that defines orientability. Then you forget the third dimension. Yeah? Now, can you patch things together and come back to the original point? Now, it's defined just in terms of ordering. X followed by y is positive. Y followed by x is negative. And that's what's going to happen if you try to take a bunch of patches on the Mobius strip. Take x, y, x, y, x, y. Then finally, when you come back, y and x will get interchanged. Okay? So, yeah, actually, it's fairly simple to see in this picture. So x is in this direction, y is in this direction. When you go along here, y is here, x is in that direction, but it's getting pasted in the other direction, right? So it's minus y, x followed by minus y, rather than x followed by y. Therefore, the orientation has switched. Good. So that's an intrinsic way of describing what orientation is. Yeah. All right. So now orientable closed surfaces, I have stated the theorem, is classified by an integer. Positive integer or 0, yeah? N, number of handles, that's what classifies. What are you studying? Yeah? Chemistry. Okay, very good. Okay, so what's an example? And there's a reason why you don't see closed orientable surfaces in R3. They don't exist. Okay? So, the reason, so what is an example of a closed orientable surface? A surface which does not have edges from which you fall off. The Mobius strip has an edge. This strip here, an annulus also has an edge. This is the edge. This is the edge. So if the earth was like this, you would still fall off. Yeah? We don't want shapes so that you can fall off the boundary. Yeah? So, but do there exist non-orientable examples of that sort? Answer, yes. This is an example. What is it? You take an annulus. Yes? Now you have two circles. Yes? One circle is going to, if you take that circle and pasted it together just like this, you would get a torus. That's something that you can see in 3 dimensions. What if you flipped the orientation and glued it? Well, the way you would have to do this is cut a little piece here, poke this actually through the surface, and then the orientation here and the orientation here would match up. Yeah. Basically, the two circles, their orientation is being reversed. And then it's being glued up. But then you'll have to cut through this. Cutting through this is not allowed in topology. Yeah? Allow yourself one extra dimension. Yeah, as I said, mathematicians do not respect human limitations of 3, etc., etc. So allow yourself an extra dimension, a 4th dimension if you like, where this intersection can be removed by moving this circle of intersection into the fourth dimension. What do I mean? You take a string, yeah, make it cut itself and lie on a piece of paper, yeah. So basically it looks like a figure of 8, yeah. If you wanted to remove the intersection, what would you do? You allow yourself the luxury of the z-axis, and this intersection you just move it up like this, correct? Take a rubber band, twist it. If you pasted it together, if you were a two-dimensional creature, that intersection would not be removable. You have this extra dimension, so you relax that intersection, move it into one extra dimension. Do the same thing for the Klein bottle. So a Klein bottle, the natural space which it would inhabit is dimension 4. We human beings are three-dimensional creatures. So the Klein bottle says, no, you are not worth myself appearing to you guys. So that's it. So you'll have to really imagine it. But it exists in 4 dimensions as a closed embedded surface. Yeah? Intrinsically it exists, independent of where it is embedded. Okay. And actually people have tried building sculptures of this in various places. So these bottles actually exist. Of course, they are not functional, but as bottles, but they do exist. That's the best we can do, is to create an intersection. All right. So now we've given you the classification. Now let's go back, as I said, that we want to classify, understand by penetrating further and further. Okay. So now let's look at the folder called sphere. Yeah. And as he was saying, there's a huge number. Almost everything we see around us is a surface of a sphere. How are we going to distinguish between those things? Yeah? And so we need a finer structure. This is like saying that, okay, so we have classified trees into tree 0, tree 1, tree 2, tree 3. But somehow or the other, almost every tree that we see around us is of the type tree T0. Right? So how are we going to distinguish between different T0s? That's the question that we are addressing now. How are we going to distinguish between two objects which are topologically the same sphere, which can be continuously deformed from one to the other? So we'll be needing a finer classification scheme. Just as living beings can be classified into insects, etc., etc., etc. But when you go inside insects, you'll have to say, this is a cockroach and this is an ant. Yeah? Both of them have 6 legs. Okay, so that's what will tell us what an insect is. Or branch body, arthropods, whatever. So we'll need something finer. So the field that we've discussed so far, where you're allowed to deform, that's called topology. And now this finer classification is what's called geometry. Geometry has a much more ancient history than topology. Forgetting information from geometry gives topology. That's how topology came in. But now we want to look into one topological bracket called a sphere and try to distinguish between the geometries of different fellows which can be deformed to each other and deformed to the round sphere. How are we going to do that? So these shapes are different at a slightly subtler level. A rabbit, where those ears you had removed the threads, that became a round sphere. So rabbit is a sphere topologically, but not geometrically. A rabbit is a sphere of genus, a sphere with 0 handles attached. That's it. Yeah. But what about the shape of the ear? I mean, it's pointed, right? It's not nice round. Yeah. And essentially, what we are going to distinguish is something that this curvature is something that you can actually feel. Yeah, not something you can see. So, for example, if you have a very sharp point and you poke it, chances are that you're going to cut yourself, right? But if you take a very blunt object, say this mic, and you poke it, you're not going to cut yourself, right? That sharpness is really recorded by this geometric notion of curvature. So we are going to try to make precise what curvature is. So geometry, essentially we are going to call it curvature. All these guys are homeomorphic to the sphere. Yeah, these are examples of from a completely different talk. These are called solids. They're called Platonic solids. Okay. All these are spheres. But somehow or the other, now if I ask you, take this object, this has got 12 faces. It's called a dodecagon. Yeah? And you look at this corner. Now you look at the corner of a square. Okay? So suppose you had this corner here. Yeah? Is that sharper or is the surface of a sphere sharper? What would you say? This one is sharper. So if you have a dodecagon, this corner here, what would you think? Is this corner sharper or is this the corner of the cube, the cube sharper? Cube is sharper. What about this tetrahedron? This is called a tetrahedron, yeah? The pyramid with a triangular base. Is its edge sharper or is the corner of the cube sharper? Tetrahedron is sharper. Very good. So we all have a common intuitive understanding of what curvature means. How are we going to make this precise? Yeah? Okay. So here's the point. We'll have to have a way of quantifying it. We'll have to introduce numbers. Yeah? Just as in this topological classification, we introduce numbers 0, 1, 2, 3, etc., etc. Here also, at a point, we are going to introduce a number which is going to measure how sharp the object is. Okay? So the surfaces of all these solids is homomorphic to the sphere. But curvatures at the vertices are different. How do you measure curvature at a vertex? How do you measure sharpness of a point? That's the question that we are posing. So if it were, what would you call something that is not sharp at all? Completely blunt. Yes, yes? Flat. Okay, so flat sets the zero of our sharpness, right? Something that's completely flat is not sharp at all. So if you take a point on a flat plane and you say divide it up into say a bunch of lines coming out of that and you measure the total angle around that vertex, how much are you going to get? 360 degrees, very good. So 360 degrees and you want to set that, say that 360 degrees is actually equal to 0 in terms of sharpness. What do? Naively subtract away. So we usually measure not in degrees but in radians. So 2 pi, yeah? 2 times pi radians. Yeah? So you take 2 pi and subtract away the angle, total angle around a vertex. That is going to be a measure of sharpness. Okay? The deviation from, if the deviation from flatness is 0, which means that the total angle is 2 pi, you say sharpness is 0. Right? If it's less than that, then the more it is away from 2 pi, the sharper it is. That degree of sharpness, so the defect between 2 pi and the total angle at that vertex is what we call curvature concentrated at that vertex. Okay? So how to measure curvature at a vertex? This is a notation. Chi is this is this Greek letter chi. Okay? This letter here. At that vertex V, chi sub V is 2 times pi minus the sum of angles at that vertex. Okay? So what is, now let's do some computations. So now we have this dodecahedron. How do we draw it? Actually these are all examples that you can actually draw on paper and fold. Yeah? So you draw a pentagon, 5-sided figure with all equal sides. Then you poke out 5 edges from them. Where you hit that, from there you poke out 5 more edges. And at each stage you join them together. You're going to get an example of this dodecahedron projected on flat paper. What is the angle at, what is the internal angle? So we want to say the following. What is the curvature at this vertex? And we want to make precise our intuitive notion that every vertex of the dodecahedron is blunter than the edge of than the corner of a cube. That is blunter than the corner of a tetrahedron. Yeah? So we want to make that precise. So let's do some computations. What is the angle inside? We want to see what we'll have to do is actually do one computation. What is the angle here? Then around every vertex there are 3 of these angles. 3 times that is going to be the total angle at that vertex. 2 pi minus that is going to be the curvature at that vertex. Correct? So we'll have a measure of sharpness or bluntness. Right? So what is the angle? So it's actually 3 times pi by 5. How do you get that? If you take any convex polygon, what is the total angle of external angles? That's always 2 times pi, right? Always 360 degrees, correct? School geometry, yeah? And so therefore, what is the external angle in a pentagon? It's 2 pi divided by 5, correct? So, but we want the internal angle. So, the external angle is 2 pi by 5, the internal angle is pi minus 2 pi by 5, right? That's 3 pi by 5 here, correct? So, that's the angle at a vertex. That's what I have said here. This theta I, the angle at one vertex is 3 times pi by 5. Therefore, what is the curvature? It is 2 times pi minus the total angle around that vertex, which is 3 times 3 pi by 5, right? So, 9 pi by 5. 2 times pi minus 9 pi by 5, that's just pi by 5, correct? So, the curvature concentrated at a vertex of a dodecahedron is pi divided by 5. 180 degrees divided by 5. 36 degrees worth of curvature concentrated at every vertex of your dodecahedron. Okay? Okay. Now, there's a reason I'll do this. What is the total sharpness of the dodecahedron? At every vertex, there is pi by 5. How many vertices are there? 12. Therefore, how many vertices are there? How many? The number of faces is 12. Okay, so that's why I said let's go back to this picture. See these layers of 5 vertices, 1, 2, 3, 4, 5, that's 5 vertices. At the next level, it's 1, 2, 3, 4, 5. The level below that is this vertex here, 1, 2, 3, 4 and 5. And behind there is one more 5. So there are 4 layers of 5 vertices each, right? So total number of vertices is 20. Yeah? Concentrated curvature at every vertex is pi by 5. Total curvature is 20 times pi by 5. That's 4 pi. Okay. So the total amount of sharpness carried by a dodecahedron is 720 degrees. 360 degrees. Yeah, that's right. 720 degrees. 4 times pi. Yeah. Okay. So the total amount of sharpness is fine. What about a cube? Now let's try to do some other computation. Let's go back to this picture. What is the curvature at a vertex of a cube? Yes? What is the angle inside a cube? And yes? 90 degrees, pi by 2. How many angles are there at that vertex? At every vertex, how many angles are there? 3. So what is the total angle around that around a vertex? 3 times pi by 2. What is the angle defect? The amount of sharpness? 360 minus 270. So that's 2 pi minus 3 pi by 2. That's pi by 2. So there's 90 degrees worth of curvature concentrated at every vertex of the cube, pi by 2. How many vertices are there? What is the total curvature of the cube? 8 times pi by 2. That's 4 pi. What was it for the dodecahedron? 4 pi. Okay, good. Experimental evidence. 2 things coinciding. Now let's look at this tetrahedron. Each face of the tetrahedron is what? An equilateral triangle. What is an internal angle? 60. What is the total angle around how many angles are there around a vertex? 3. What is the total angle around a vertex? Pi. Pi by 3 plus pi by 3 plus pi by 3. 180 degrees. That's pi. What's the angle defect? Yes? Pi. Yeah. 2 pi minus pi, pi. How many vertices are there? How many vertices are there of the tetrahedron? 4. So what's the total angle defect? Yes, yes? 4 times pi. So that's 4 pi. So that's again coincides with what it was for the cube, what it was for the dodecagon. Yeah? Now we've done 3 of them. So what is it? So what is the measure of sharpness? So for the tetrahedron, sharpness at a vertex is worth pi. Pi's worth of sharpness is concentrated at every vertex of a tetrahedron. Pi by 2's worth of sharpness is concentrated at every vertex of a cube. Pi by 5's worth of sharpness is concentrated at every vertex of the dodecahedron. Yes? If you took larger number of faces, there's a picture here. This is called the icosahedron. Yeah? It has 20 faces. Yeah? you will see that the angle decreases. But the total amount of curvature, oh, here's something. This is two pyramids with the same thing, glued base to base. Yeah? Okay? That's right. That's right. Okay. So, yeah. So what is, okay, so shall we do this computation also for this? I haven't done this before. Let's do this. For this, I think it's called a octahedron, right? Yeah. So it's 8 faces, octahedron. So what is, let's do this computation. So what is each face of that? That's a equilateral triangle. Angle is 60 degrees. Yeah. How many faces around a vertex? 4. 60 into 4, 240. Angle defect 120, right? So 120 is larger than 90 degrees, but is less than 180 degrees. So it's sharper than a cube, but not as sharp as a tetrahedron, right? But what is it? So what is the angle defect? 360 minus 240, that is 120. 120 into, how many vertices are there? 4 and 2, 6. 120 into 6 is 720, 4 pi. So we have computed angle defects, that means degree of sharpness at a vertex. Somehow or the other, when we sum the total amount of sharpness on either the dodecahedron or the tetrahedron or the cube or the octahedron, we get the same answer 4 times pi. This seems too much of a coincidence. Okay?
Professor, but does it make any difference if you take individually at the vertex, the sharpness is more or less, like for each one is different?
Yeah.
The total is the same. So in any way, all these 5 are related?
Answer. This is the answer. Therefore, total angle defect is this. So fact. Here's the theorem. The total angle defect for any cellulation of the sphere. You take your sphere, divide it up into cells, flat pieces. Yeah? Okay? Compare, if you have a flat piece, then you have a Euclidean polygon. That angle, so you can measure the angle at a vertex. Take the sum of all the angles at a particular vertex. Look at the angle defect. Doesn't matter if your cellulation is regular, irregular, how badly irregular it is, doesn't matter. The total angle defect, total amount of sharpness, which we also call total curvature, is going to be always equal to 4 pi. This is a theorem by somebody called Gauss. Okay? From about 7, yeah. Yes, please. For the tip of a cone, a tip of a cone is not a polygon. There is no way of saying what the curvature concentrated is in that sense. There is a way of saying it, but see, a cone you will have to unfold, right? If you unfold a cone at that point, then there is going to be an angle. That angle, what would it have been if it was flat? It would be 2 pi. So 2 pi minus the cone angle will be a measure of the sharpness of the cone tip.
But there should be a measurement for it.
No, that's what I'm saying. Any cellulation means any polygons. Take a sphere, build it up out of flat pieces of paper. Just a sec. Build it up out of flat polygons. Convex, concave, anything you like. Each piece must be flat. And it must be a polygon. Doesn't care what it is. Yeah? The total angle defect is always going to be equal to 2 pi. So this is called the polyhedra. I'll say a little more about this. Okay, let's keep it at that slide. Finish off this question. Yes?
You take a square cube and remove another square, another cube from inside it.
What do you mean remove another square from inside it? Yeah?
And then you take another cube inside that cube.
Inside that cube means you are looking at a 3-dimensional object. A 2-dimensional object does not have something inside it.
No, okay, so you take a cube, which is but then you make a cup out of it.
Okay?
And by that's what I mean by removing another cube.
So you take a cube and you take a drill a hole from the top to the bottom. Yeah, so a square hole from the top to the bottom drilled. Yes? Yeah. So what will be the angle defect there? So, okay, so what you are saying is that instead of, what he is saying is the following: instead of doing it on a sphere, do this cellulation on a torus. If it doesn't go through and through, oh, it just sits like a cup, it's a cubical cup, then also it's a sphere, right? It's deformable to a sphere. No, no, each vertex does not have the same property. At the places where it's concave, it's got negative angle defect. It's got minus pi by 2 angle defect. That minus pi by 2 and that plus pi by 2 will cancel off. 2 pi minus the total angle. That's what's important. At each of the top 4 vertices where you have dug in, it's pi by 2 plus pi by 2 plus pi by 2, and then there is a 3 thing. See, if you locally, what does it look like? You have around this vertex, you have one square here, one square here, one square here. And then you push it in, there's one square hanging like this, one square hanging like this. So it's 5 times pi by 2. That's the angle sum around that vertex. 2 pi minus 5 times pi by 2 is minus pi by 2. Go do the exercise at home, you'll get the same answer. Okay. Okay. Yeah, yeah. I mean, well, no, not really. Otherwise, we would not be using arrows. Yeah.
No, symmetric polynomial.
Symmetric, yes. If all the vertices have to have the same angle defect, the same curvature, then the answer is that the sharpest is the tetrahedron. Yeah? But I mean, the reason why people used arrows is because they wanted a very sharp tip, very highly curved tip. Yeah? What is the maximum curvature you can get concentrated is when you have a needle. That's entire 2 pi, the total angle sum is 0 for an ideal needle, one-dimensional needle. The total angle defect is 2 pi. So that's the sharpest you can get. Yeah? Yeah? No, you don't do the calculation when one of the faces is a circle. You do the calculation when all of them are. Otherwise, you don't have a notion of angle concentrated at a vertex. You don't have, one can generalize all this. One can smooth it all out, and then one will have to pass from a sum to an integral. I don't want to do that. Essentially, the theorem way it was stated originally is in terms of an integral, but if you discretize this whole thing, it's just a finite sum. Okay? So here's the thing. Let's, what's your name? Yeah, well, so Ishan's question, let me try to extend it to a more, to a setup where you'll get something different. Suppose you take one of these tori and you build up your torus out of square pieces, yeah? So you take a cube, take a small cube in the center of that big cube, yeah? Drill it all the way through the cube, then you have a torus, right? What will be the sum of angle defects for that torus? That's not going to be the same as that for a sphere. Okay, and here's the general answer. This is called the polyhedral Gauss-Bonnet theorem. Essentially what you will get is, look at the number of handles you have added. Now we are tying it up with the topology that we had done at the beginning. A sphere with n handles is what you get in general, right? Take, if the number of handles is 0, then you get 2 times 0 minus 2, that's minus 2. Multiplied by minus 2 pi. So for a sphere, you get minus 2 pi into minus 2, that's 4 pi. For a torus, you have 1 handle. So you have 2 into 1 minus 2, that's 0. So for a torus, you are always going to get sum of curvatures equal to 0. For that 3-handled teapot that we had, if we made it into flat pieces, what we will get is minus 2 pi 2 into 3 minus 2. That's 6 minus 2, that's 4 inside. And you're going to get minus 8 pi, yeah? So for whenever you have the number of handles exceeding 1, the total angle defect is going to become negative. This is the formula, minus 2 pi times 2 times the number of handles minus 2, which means what? The topology of the ambient object, the number of handles you have added on with, yeah? That and this total amount of geometric curvature, the amount of curvature might differ from point to point. But if you sum it all up, you get something that's a topological invariant. Okay? So whatever be the sphere that you take, a stone, take a lemon, take something and do this sum after dividing it into small flat pieces, you're going to get 4 pi, always. If you did it on a donut, you're going to get 0. You do it on a pretzel, you're going to get minus 4 times pi, and so on. So I'll stop. That's it. Thank you.
Yeah, questions? Anything at all? We had a lot of discussions as we were going along, Arkan. But this, when you say cellulation, that means...
Cellulation means dividing it. A cell is a 2-dimensional polygon.
Okay.
Cellulation means, triangulation means dividing it up into triangles. Squareulation means dividing it up into squares. Cellulation means dividing it up into cells. What is a cell? A cell is a polygon.
Yeah. A cone, as was pointed out,
a cone is not a cell.
Is?
It's not a cell.
But it's still topologically a sphere, right?
That's right. So, but in order to do this angle defect computation, the topology is not important. What is important is the actual geometry. So, you have to compute in terms of summing angles. If, say, for example, you have a round sphere, yeah, you push it down flat. What was there was a curve. So, a square had curvature concentrated at a vertex. When you push it flat, there is no curvature concentrated. So, curvature is something locally is not a topological invariant. Locally, at a point, you take a sharp, I mean, that's why we get hurt by arrows and we don't get hurt by flat things coming and hitting us. You just take the surface of a cone and you flatten it out and you hit somebody with that. That's not going to hurt. Which means that somehow or the other, our nerves sense curvature. Yeah. Curvature is a local object. Yeah. If you change it by retaining the topology, the curvature is not going to remain the same. A sphere is topologically the same as a cube. It's the same as a tetrahedron. It's the same as a dodecahedron. But the curvatures at vertices are changing. What is not changing? The total amount of the curvature.
Yeah. Yeah, in fact...
so, locally there is a change, globally there is no change. Yeah. And this global non-change of geometry is phrased by saying that the total amount of global geometry is a topological invariant, though locally it is not.
Yes. Yeah, I've never heard it explained so lucidly. Raghunathan has something.
It's just I have a small remark or a comment and then a question.
Yeah.
So if we think of a coffee cup, and if we have its handle broken, we have objects that are two different topologies, but we can still use them to drink coffee.
Yeah, of course.
But if we take a coffee cup and extend the bottom, the object has the same topology, but we can't use it to drink coffee. So the now question is, could you please say some examples?
Functionality has nothing whatsoever to do with
Sure, definitely. So the question is that, could you please say something about different domains of science where topology is being applied and how it is being applied?
What is happening? Yeah. The coffee cup with the handle is a torus. The coffee cup with the handle broken off is a sphere. The coffee cup with the bottom broken off is a genus 2 surface. So those topologies are completely different. Okay. So there are 3 different topologies you are getting in the process. Where is it useful? Where is this notion useful? Okay. So I'll tell you where it's useful in physics. So suppose you want to, suppose you have a material, and you have, say the material is arranged roughly in the form of a crystal, and then you have, so the material has, say, defects in it, which means that some molecules which are supposed to be there along the lattice have been replaced by something else. Yeah? That contributes a little charged sphere around it. It distorts the uniform chargelessness of the ambient thing. Yeah? You can do this summing process on the surface. You chop off a big piece of that, you do the summing process of the outside, and it will record for you the number of defects you have inside. Okay? So the number of defects, if you had to go into the material and look at it, then the material will be completely destroyed, right? Instead, what you do is you take the material, do some measurements of charges, do this sum of the stuff only on the surface. Yeah? What do you infer from that? That each defect contributes to some topological information on the surface. That total sum, exactly this Gauss-Bonnet theorem. Yeah, that actually you do it in the form of an integral, and that is going to give you the number of defects. So if you want to reduce that, then you have to reduce some more. Yeah? So whether you have an appropriate material or not, that can be done by this very precise same technique. Yes, you had a question.
Get the distorted feature. Could you get the torus attached to the sphere?
Yes, and then that sphere is a sphere, that sphere you can always shrink down. See, a balloon which is long and thin and a balloon which is nice and round have no difference as far as the topologist is concerned.
By coding this, the fundamental unit of any material should be spherical.
That the topologically the most uncomplicated two-dimensional surface is a sphere. That's what you can say, not unit. If you want to see, a torus is not built of spheres. It's a different object from a sphere. You take two different spheres, it's not a torus.
And from the material perspective.
What is the material perspective? I am sorry, I don't have it.
Can you extrapolate that by this theorem? An atom should be spherical.
No. An atom. Now we are going into models. That's again a very different story. Yeah.
Because at the tip of that arrow, something is here, but it is made up of some.
No, that's the whole point. Do you see? Is the number 2 made out of some material? 2 trees, 2 human beings, 2 chairs, 2 bags. Is the number 2 made out of any of these materials? No. Just try to understand this issue. The number 2 is a mental abstraction. It is the property that is common to 2 chairs, 2 tables, 2 trees, 2 human beings, 2 bags. So once you do that abstraction, it does not care whether it's 2 bags or 2 trees or 2 chairs, right? Similarly, when you're talking about a sphere, it can be a sphere made of cloth, it can be a sphere made of rubber, it can be a sphere made of the most expensive material on earth. One does not care. The material is completely irrelevant. The sphere is an abstraction. You can say a spherical balloon, a spherical shirt, a spherical fabric, a spherical design, etc., 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 etc. The material that you use to build it up is completely irrelevant. There is no material. The material is the human mind. Common features of the human mind. That's the material we build it out of. Just as 2 is a mental abstraction. You don't see 2 anywhere outside. Yeah? It's an abstraction. Yeah? It exists only in the human mind. Yeah.
You see, like, most of the Indian kids, our geometry is regular, like your IIT type, everything and all. But this beauty of mathematics, how you can introduce at the lower level. I'm not talking about the PhDs and all everything. So those suppose somebody wants to go to the beauty part.
I think if you want to really show what is beautiful about mathematics to young minds, there are 2 avenues and 2 avenues alone. One is beauty of natural numbers, counting, that's the first abstraction. The other is geometry in terms of classical Euclidean geometry. There's Hall and Stevens, all those are beautiful books. Yeah, I mean, I think some people here must have at least read those books when they were students. I certainly did. And those riders, essentially problems to prove such and such in a geometric theorem, that's actually the best training in formal reasoning that one can get. I think there's one book by Pomeranke, which is a relatively more recent book. Which
the practical side of mathematics. I just went to New York. They have a museum of mathematics. So and all practical mathematics, not your equations, this one, that thing, all your circles, everything they did practically.
Yeah.
So is there any way that we can do it in India?
Oh, I think there are people who are doing it.
Like a museum type.
There are, okay, so I'll suggest one thing that you can do. You take a rope, yeah? Take just a slightly thick twine, yeah? Take a square board and start pinning your twine down there in some extremely complicated shape. Then finally the 2 ends you splice together, yeah, in one place. Now take a random point on that square. Pick a point and ask the question, is that point inside the circle that you have drawn or outside it? There's a non-trivial amount of topology and you can count it fairly simply. The answer is you take that point, take a scale so that the other end of the scale is outside. Look at count the number of intersections. If that number of intersections is odd, it's inside. If it's even, it's outside. Yeah.
Can you let us know if there is a very layman-like question that layman can attempt, like in the college, just to get a feel of what it could be to challenge this, to take up a small challenge?
Okay. There's a version of this question which sounded very layman-like. Yeah. This is a two-dimensional thing. Yeah. So there's a notion of simple connectivity. What is it? You take a rubber band on your surface, and if you can contract it to a point, then for any rubber band, then your surface is called simply connected. So a sphere, surface of a football, you stretch a rubber band around it. By staying on the football, you can contract it to a point. If you have a torus, you can't do that. You put a rubber band around it like this. You can't. Thank you. You can't contract it to a point. Three-dimensional version of this question. Instead of something that is closed two-dimensional, take something that is closed three-dimensional. Yeah? Three-dimensional. That's called a closed three-dimensional manifold. Closed three-dimensional manifold is simply connected. Is it only the three-dimensional sphere, x square plus y square plus z square plus w square equal to 1? Question. Sounds very naive, right? Just one half an hour or 45 minutes of a topology thing and you can pose this same problem in one higher dimension. So it was posed in 1905 or so by somebody called Poincaré. It became called the Poincaré conjecture. It was solved about 100 years later and it got the Fields Medal. Fields Medal is the mathematics Nobel Prize, yeah, by somebody called Perelman. Yeah. So from something very naive like this, you take one more step, you get to a very famous problem. I don't know how many people in India actually know a proof of that theorem after it has come out. So yeah, I mean, problem something that can be phrased or worded simply does not mean that the solution is easy. Yeah. 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 No, Mandelbrot talks about fractals in terms of complex dynamics. I don't know what article of Mandelbrot you are referring to. Yeah, that's right. So fractals are a completely different thing. They are objects that live inside the complex plane. Okay? Yeah, so that was actually the subject of my talk yesterday.
And Professor Mahan Maharaj gave a talk at TCIS yesterday, and there he said that, and if the natural world does not conform to this, too bad for the natural world. So the fact that most of the things that we see around could be probably described as a sphere or a torus is a limitation of the natural world. Actually, mathematics goes way beyond that, and that's quite humbling for some of us who are in the natural sciences. So there have been many sawal jawabs here where we ask, so what is this useful for? But here, of course, this is useful for many things, but beyond that, this is about something about the fabric of the universe and the world around us, which is not captured in the natural sciences, and it's very exciting to hear about this.
Yeah, so I think the best answer to the unstated question there is a comment by this somebody called Wigner. So it calls this the unreasonable effectiveness of mathematics. Yeah. So mathematics as a discipline, I mean, what are the criteria that help us build mathematical structures is essentially these abstract objects and how they fit together as abstract structures per se. And experientially, just something that has told us over maybe thousands of years, is that if an abstract structure has something that is deep in it, which means if it ties up with more than one area, sooner or later you will find some application in the real world. Let me give an instance. This is my favorite example. Many of you use a GPS today, right? So the GPS incorporates into itself what are called general relativity corrections. If you travel for maybe say 1,000 kilometers and you have not corrected the GPS using general relativity corrections, chances are you are going to go one street off. Okay? Make mistakes in your GPS. General relativity was discovered by whom? Einstein. When was this? Say in the early 1900s. So it's finding an application in a day-to-day thing today, 100 years after that discovery. Good. What was the mathematical structure behind Einstein's general relativity? Pardon me? No. It's something called Riemannian geometry. Yeah. So hyperbolic geometry is an example of that. When was that discovered? That we don't know. That was 1840s or 1850s. Yeah. The problem that was posed by this same Gauss posed a problem of trying to understand, I think one of you asked this question, what is geometry in dimension higher than 2? Gauss had worked a lot in two-dimensional surfaces. What is geometry in dimension higher than 2? There was not even a language to talk about geometry in dimension higher than 2. And the person who encoded that entire thing into one package was Bernhard Riemann, one of the finest geometers of all time. And he encoded how you are going to compute it, because you can't see things in more than 3 dimensions, human limitation. But you still want to compute with it, you want to deduce conclusions about it. So he came up with the notion of geometry in arbitrarily many dimensions with arbitrary curvature properties. Riemannian geometry. And a small generalization of that is what is called Lorentzian geometry. This is the mathematical backbone of all of general relativity. Einstein learned that from a mathematician friend of his. And then that was the tool that became useful there. It becomes useful as your GPS today. So the mathematics that was discovered 150 years back becomes useful in a very tangible way today. So this is again one more instance of the unreasonable effectiveness of mathematics. Why did Riemann come up with it? Just because it was a very natural mathematical structure. So there is a mathematical nature that we want to probe. So we have a sense of what structure is deep in mathematics per se. Invariably, after all, it's human beings who drive cars, use GPS. It's a human being that does theoretical physics. It's a human being that thinks of mathematics. So at a certain more abstract level, one can understand that even if there's some deeper structure in mathematics, it's going to be relevant somewhere else. But that depth, as a criterion that you evaluate yourself, has to be just the way people who like classical music understand that this is a deep piece of music. Yeah. So taste that one has to come. Yes?
No, I mean, I was just wondering if that is not really quite like the formatting power of mathematics. At one end, the science itself is heavily shaped by mathematics. Yeah. And that you are finding something in mathematics that actually meets some need in science isn't surprising.
Yeah, exactly. It's not surprising. However, I mean, what is surprising is that very abstract structures for themselves, for which you have no relevance in the real world, all tied together, and you investigate something, you get some facts, get some theorems, suddenly starts appearing in a completely different garb and becomes a rich structure. So this was one example. The next major revolution was in another field of theoretical physics called string theory, where certain manifolds called Calabi-Yau manifolds become very important. These were discovered by mathematicians maybe 2 or 3 decades before they became important in physics. Those guys are string theory is still to find its way into even experimental physics. Maybe it will find some use in practical terms maybe 100 years later or something like that. Yeah. So at a certain level, because human beings are doing all this stuff, it's not surprising. But in very, I mean, it starts suddenly appearing in a completely different garb, in a completely different area. That is what's surprising. Yeah.
Can I just...
Yeah.
Hi.
Oh, hi.
Can I just try to put it in one way, that when we limit ourselves to objects, we are limited by 3D, the torus and sphere type.
Yeah.
But when we are talking about an ensemble of observables, which we may or may not know how to cluster and how to classify.
Correct.
an earlier presence of a structure mathematically helps us to cluster those set of observables and put forth a more general theory.
That's right. That's right. That's right. That's right. So there's so what Vijitha was saying is there's a interplay between two things from two different directions. One is once you have a mathematical tool to organize, the temptation is to use it, right? Otherwise, but what is really very astonishing is that sometimes these coincidences happen. Somebody writes down an equation and then somebody comes along and looks at it. These coincidences happen within mathematics also. Yeah? And say, oh boy, this structure has appeared somewhere else. And whenever you see the same structure occurring naturally in two different parts of human pursuit, yeah, it shows that there is something deep going on. Yeah? What is it that unifies these two fields of knowledge? That question immediately comes to mind. Yeah? Is there such a unification, or is it just a coincidence?
I mean, I don't know if geometry across cultures have been, have the same approach. And if, say, for example, I have read a little bit of geometry in India, but very little bit, I would say. It's very different from the Greek geometry.
Well, I'll say a qualified yes to that question. So, for example, the way it's stated is somewhat different. Yeah. But say, for example, Sulva Sutras, which were discovered in India, and Pythagoras' theorem, they state exactly the same thing in different languages.
Pythagoras' theorem has been there apparently for quite some time, but the facts, for example, sir?
Second example, I'll tell you. Second example is the area of a triangle, S minus A, S minus B, S minus C, square root, etc. by 2, whatever. That was discovered in two completely different places. This is not the kind of coincidence I'm talking about. This is two cultures coming up with the same fact. Yeah? What I am talking about is something else. What I am talking about, say you have, in physics today, you have this tool, it's something what's called the gauge geometry duality. Yeah? Quantum mechanics, one field of physics, goes on by trying to understand gauge theories, fundamental forces of nature apart from gravity. The other fundamental force of nature is it has to do with geometry, has to do with gravity. One writes two ways of understanding these two radically different physical theories in two different worlds. Suddenly they seem to be giving the same thing. Conjectural, then you conjecture. This is something called the ADS-CFT conjecture. It's a very major engine driving research in string theory today. So, you have two things coming in completely different areas of mathematics or of physics. And the same structure emerges. Yeah. And if that same abstract structure emerges out of very different contexts, say for example, somebody is playing around with molecules. Yeah. And then say doing biomolecules or genetics, right? So you have this double helix structure of our human DNA. Yeah. Now, you have, say, people braiding strings, yeah, and then getting some abstract mathematical structure out of braiding strings together. Suddenly, in 1980s or 90s, it was seen that, oh, okay, all this DNA material, the structure organizing it, and the abstract structure in mathematics doing what are called these braiding operations, they are the same. Something has its origin in biology, something has its origin in completely abstract mathematics. Suddenly it's coming together. How? Why? We don't have an explanation, and it's really one of the it's an exciting thing for a scientist. Okay, some stuff that which I was really interested in is actually of interest to some completely different set of people.